All right, moving on to one of these AP style questions here. So we have this situation set up where we have a string, 4 strings tied to 4 different oscillators, and there's a mass on the end of each string that is the same. Okay. And so these oscillators are adjusted to vibrate the fundamental frequency for each string. And we see we have 4 different fundamental frequencies here, ranging from 350 hertz to 400 hertz. All right. And it tells us this equation for the velocity of a wave on a string. All right. We didn't really talk about this, but we're given this equation so we can use it. So Ft is the tension in the string, and m over L is what's known as the linear mass density, the mass per length. Okay. So first question here is, what is different about the 4 strings shown above that result in them having different fundamental frequencies? Okay. So we know they all have the same length. Okay. So that's not changing. We know that they all have the same mass on the end of it. So that's ultimately going to lead to the same tension. So the only thing that would be different is they must have a different velocity for starters, because they have the same length but a different fundamental frequency, and that's going to result from a different linear mass density. Okay, the strings must be different thicknesses or something like that, and that's going to change the velocity of the waves on those strings. So just to explain this a little bit further, they have to have the same wavelength because they're all the fundamental frequency and they have the same length. They all have the same tension because they all have the same mass hanging off the edge of it. So they must have a different velocity from that m over L, that linear mass density term. Okay, and that's going to ultimately change the frequency. Different velocity, same wavelength, different frequency. So for part B, we graph frequency as a function of the inverse of linear mass density. We want to know if the graph will be linear. So I'm going to start with what we know. We know that velocity is equal to the square root of f of t over this m over L, that linear mass density term. And I know I want to get my frequency in here, so I know velocity is simply wavelength times frequency. Okay, is equal to the square root of f over t divided by this linear mass density. So what I'm going to do is I'm going to go ahead and isolate the terms that I really care about. Alright, so we're going to have some constant wavelength here times that frequency is going to be equal to the square root of f over t, alright, and then times what remains here, that term I really care about, 1 over the square root of m over L. So these are the 2 variables that I care about. So we graph frequency as a function of the inverse of linear mass density. This will not be linear. Okay, what we ultimately need to graph is we need to graph frequency versus the square root of that inverse to be linear. Alright, moving on to our last one. It's with this diagram here for part C. And now we're told that the string vibrates at its second harmonic, alright, which means that we're going to have a node directly in the middle of this wave here. Okay, so something like this, right? So our waves, if we're thinking about them, are going to be like that, right, when we create those standing waves. So we want to indicate the points that have the greatest average vertical speed. Okay, well, those are going to be those antinodes, which are going to occur here, and they're going to occur here. Okay, right in the middle, we're going to see the greatest movement of the strings to the greatest average vertical speed. Alright, moving on to the next one. This was actually one of the AP problems from last year's exam. So the figure on the left shows a uniformly thick rope hanging vertically from an oscillator. When the oscillator is on and set at a certain frequency, the rope forms standing waves that we see over here. Okay? And so we have these 2 points on the rope, P and Q. The first question is, why is the tension at P greater than the tension at Q? Well, this is a case, and this is something we usually ignore. We usually ignore the mass of the rope. But in this case, we're not going to be able to ignore the mass of the rope. Okay? Point P must support all the rope below it. Okay, so would point Q, because the rope itself now has mass, so we need tension to support that mass. And since point P has more rope below it, it's going to have a greater tension. So there's going to be more rope below P, like I said, which means we need a greater tension to support all of that weight, to support that force of gravity. All right, so now we have this student who hypothesizes that increasing the tension of the rope increases the speed at which waves travel along the rope. And we want to explain how this example, this diagram here, supports that hypothesis. Okay, so the first thing that we notice is, velocity, and this is really from the first part, at point P is greater, based off of this hypothesis, because our tension is greater at point P. We explained that in the first part. So that's the first point we want to make, okay? Obviously, we want to explain this in a paragraph, but that's the first point we want to make. The next point that we want to make here is that our wavelength is greater at point P as well, okay? And we can see that just from looking at this diagram. Our wavelengths are getting smaller here than they were up here. Okay, and then lastly, all right, this is going to support this hypothesis that the velocity is greater at the top because that greater speed should lead to a greater wavelength, since the frequency is going to be the same throughout the rope, right? The rate at which those waves are being created, how frequently those waves are passing, is not going to change even if the tension and the wavelength changes. Okay, for this problem here, we have two wave pulses that are traveling in opposite directions, and we see what they look like at time t equals 0. That's right here. Each one of them is traveling at a speed of 1 unit per second, so it's going to advance one of these grids here every second. So there's two things we want to do. The first is we want to look at the velocity versus time, the vertical velocity versus time of the string at point P here, which is this location right here. The second thing we want to look at is what they look like when they eventually overlap, which occurs at t equals 5 seconds. So the first thing I'm going to do is I'm going to advance each one of these pulses ahead 5 seconds. That would represent where it's going to be when we eventually have this intersection, this overlap. So we're going 1, 2, 3, 4, 5 with that pulse. And so that pulse is going to be located right here. And it's going to look like this. Okay, and then we'll do the same thing with the other pulse, advancing that 5 seconds, 1, 2, 3, 4, 5 to that point there. We do see that they completely overlap at those points, and that pulse is going to look like this. So all I did was just move them ahead 5 seconds. Okay. Now I'm going to think about what this velocity versus time graph is going to look like here. So from 0 to 1 seconds, right, and each time we're thinking about point P. So from 0 to 1 seconds, the pulse will move from here to here. What we see is this segment that moves through point P has no amplitude whatsoever. So that means that there is no velocity there for point P during that time. Then, during the next 2 seconds, this part moves through. Okay, and so point P rises up to a maximum height of 2 centimeters over a period of 2 seconds, all right, from 1 second to 3 seconds as that segment moves through. And so that means the speed of point P during that time is going to be a constant speed of 1 centimeter per second. Okay, and so we have that right there. So there's my speed of positive 1 centimeter per second as point P rises up to a height of 2 centimeters. We then drop back down over the period of 1 second from 3 seconds to 4 seconds. We drop down 2 centimeters in 1 second, so that's going to be a speed of negative 2 meters per second. So that's going to be down here. And then finally, the last segment that moves through is this part right here. It's completely flat, so we're back to 0 meters per second. If you connected the dots, that's okay there, but the key is really having those horizontal lines. That's the important part. So for the last part here, we want to draw what the composite wave looks like, what the superposition looks like when the pulses completely overlap. And so we're going to go ahead and do that. And the first thing I'm going to notice is when the two waves are in this position, so remember they're not here or here anymore, when they're in this position from 0 all the way to 1 unit past P, there's nothing, all right? And so that's going to be very easy. That's just going to be 0 to that point there. We also see that from 3 units, 1, 2, 3, beyond that to the end, okay, we also have nothing. And so from this point here all the way to the end, it's just going to be 0. So that's the easy part there. I'm now going to think about specific points while they're overlapping. I'm going to take this segment by segment. So for this first segment, this wave, okay, this line here is going up at a slope of 2 units, 2 centimeters per 1 unit. This one's going down at 2 centimeters per 1 unit. And we can actually see here that these two lines, -2 and +2, they're going to cancel each other out completely. So this next segment here, all right, there is a superposition occurring. There is a wave there, but that's destructive interference. They're canceling each other out. For the next segment here, from here to here, okay, they don't mirror image each other. They're not going to completely cancel each other out. So what I would think about is where we are at the end of that. So here, the green one is at -4. The blue one is at +1. And we're going to add those together. That's all superposition is doing, is adding them together. -4 plus +1, that leaves us at -3. So we need to be at this point here, all right, when we get to the end of that next unit. And in between, we're just going to see that that wave is slowly going down. Okay, the green wave continues on down at a rate of 2 centimeters per unit, but the blue one also starts dropping down, and that results in a wave that looks like that. That last little part there, we eventually need to get back to 0 here. It's a very similar situation, except now our wave is growing. Okay, the green one's growing, the blue one continues decreasing, and we can just connect that final dot there. And so we get a composite wave that looks something like that. And that's what it would look like when those two waves overlap. I think the easiest way is to plot points. Okay, and that at least gives you the general outline there, and you can kind of fill in the dots from there, or fill in the lines from there.